Welcome. This video is going to look at Section 5 from Chapter 4 of the Brown SL Chemistry book, and Section 5 looks at metallic bonding. Metals have low ionization energy, so they generally lose electrons to get stable. So if they can transfer them to a nonmetal, that's great, and an ionic bond results. But if they don't have a nonmetal around to lose them to, then sharing doesn't really work so well. So a traditional covalent bond doesn't really help metals out. So what metal atoms tend to do is they bond to themselves, so the same element, and they form these metallic bonds that are somewhat similar to ionic bonds, although they have some similarity to covalent bonds too, so they get their own name, metallic bond. But what happens is these pure metals are loosely holding their own valence electrons. And if there's not a nonmetal around for them to wander off to or get pulled off to, then they just kind of wander off within that pure metal substance. And that leaves behind a positive cation, which is the nucleus and the inner electrons. And these positive cations tend to line up in a lattice, just like ionic compounds do. So you've got this very structured lattice of just the cations. The electrons then are delocalized or free to wander among the cations. And it's really kind of a free-for-all as whose electron, belongs with who, because electrons are all identical. Okay, so they're free to wander among the cations and bring greater stability to the whole structure, but they're not held so loosely that they actually wander off. So that's what a metallic bond looks like. So how strong is a metallic bond? Well, typically they're not as strong as ionic bonds, but they're much stronger than covalent bonds. And the strength is going to depend on the number of delocalized electrons that it has, and that's a direct result of how many valence electrons it has. The charge on the cation will also increase. So if the charge on the cation increases as your nuclear charge increases, and so when your number of delocalized electrons goes up, the charge in your cation also goes up. So those two things kind of give you a double bonus in the area of strength. And then when the radius of the cation decreases, smaller metals will tend to make a stronger metallic bond. And melting point is one indication of metallic bond strength. So an increase in melting point typically indicates a stronger metallic bond. That's one way we measure it or can get a quick idea of it is looking at those melting points. Melting point we see decreasing down a family because the radius is increasing. And transition metals tend to have really high melting points because now you've got all the electrons from the d orbital that can also become delocalized and get into that big structure. So what are the properties of metallic bonds? Well, all the metallic properties can be explained by this freedom of movement among the electrons. So for example, metallic bonds or metals are good conductors of electricity. That's because the electrons can move through the metal in response to an applied voltage. So if you hook up a power source, you can get those electrons moving, and that's electricity. They're also good thermal conductors, or conductors of heat, because the delocalized electrons are closely packed to each other along with the cations, so that allows for efficient transfer of heat. Remember, heat is just the movement of electrons, and where they're moving more gets transferred to where they're moving less. So with things packed in tightly and in this very regular structure, it allows for heat to easily be transferred as well. Metals are also malleable. They can be shaped under pressure. And that's because when you apply a force to a metal, you don't disturb this rigid alternating pattern of positive and negative cations. Instead, you might disturb the rigid structure of the cations, but they're all positive. So pushing the cations into a longer rigid line really doesn't matter than having them, in two layers. So the delocalized electrons have this random non-directional movement. They can just fit in wherever between these cations. Metallic or metals are also ductile. They can be pulled into threads or wires. And again, that's because the delocalized electrons have this random non-directional movement, so you're not going to disturb a set or rigid pattern. You rearrange the cations and the electrons just flow in where they need to be. The high melting points are because the delocalized electrons are held tightly by the lattice of cations, so more delocalized electrons, there's going to be more force holding it together. And then finally, the shiny and lustrous appearance is because the delocalized electrons are able to reflect light. Finally, when talking about metallic bonds, we need to talk about metallic mixtures, which are known as alloys. So a mixture of two or more kinds of metal. Now, technically, it could be just one metal with carbon, which is a nonmetal, also qualifies as an alloy, but typically it's more than one kind of metal. And it's made by mixing the metals in their molten or liquid state so that different atoms can mix or combine. And then as the molten alloy cools, the cations of the different metals are scattered throughout the mixture. And again, the delocalized electrons for each metal can interchange because electrons don't identify with a specific atom. Electrons are identical. So now you have basically two different sets of metallic bonds just kind of interspersed or intermingled. And again, this is because delocalized electrons are non-directional in their movement. And the other thing helping out is different sized cations in the lattice doesn't disrupt the lattice like you would expect it to. And again, that's because the delocalized cations can just fill in and help with that space. So the alloy will typically have properties different than the metals that make it up, but it's usually stronger and more resistant to corrosion, and they're usually what we call enhanced properties, or the best of each metal comes out in that alloy or mixture.